I said last time about needing to push a button to do some marking. Of course, I had to build the button. I built it this morning. I've started pushing it. Hopefully, the week 4 test has been marked. Actually, if you have a smart device, you could just see whether you have a score there. I'd be grateful because I don't get to see exactly what you see. Right. What else is going on? How much time have I got? A reasonable amount. So I very quickly did a spot of type inference last time, and I could tell it was too quick. So what I want to do is infer some types more slowly. So let's see what we had. Right. Quick recap. I wrote down these 2 rules, which are the whole of the problem with doing figuring out types for lambda terms. There's like 2 ways in which we could be working. We could either be trying to figure out, given a term, figure the type out, or we could be given both the term and the type, and we could be asked just to check whether that's right. So one of them we call type synthesis, that's figure the type out. One of them we call type checking. That's where the type is given, and you're just trying to say yes or no. Okay? So the rule for lambda is okay if we're doing type checking, right? If somebody gives us this type, sigma arrow tau, for this lambda term, then that tells us what sigma to put in the context for the variable. And it tells us what type to check for the body of the lambda. So if this type was given up front, we'd be laughing. On the other hand, if we were trying to figure this type out, do type inference, then somebody just gives us this lambda term. We don't know what type to put there. So we've got to come up with something. With application, it's the other way around. If we're doing type synthesis, then we can synthesize the type for the function, and we hope it is an arrow type. We can synthesize the type for the argument, and we then need to check that the argument type agrees with what's left of the arrow in the function type. But then it's very easy to synthesize the type of the whole thing, because that's just the result type of the function. So type synthesis is really nice. Type synthesis works really nicely for application. But if we're doing type checking, if somebody says, check that this application has type tau, we don't know what type to check that the function has. Again, we're in this awkward situation where there's a sigma showing up above the line that didn't arrive with us below the line. So we have to get it from somewhere. So the point is that if we are doing, if we're committing to doing type synthesis, we're going to get screwed by the lambda rule. If we commit to doing type checking, then we get screwed by the application rule. Either way, we get screwed. Isn't that wonderful news? So there are various things we can do about it. There are stupid things to do. Well, when I say stupid, things that require no cleverness on our part. Actually, it is quite clever, but it's the kind of clever that avoids hard work. I don't know if we've shown you, there's a way of splitting up the grammar of lambda terms, which means that, well, let me just find the document, assuming I haven't lost the document. That's the wrong document. Where's the right document? That's the wrong document. Maybe I will just have to recover it from the depths of my brain. No, here we go. Here's a grammar for you. So the thing about this grammar is designed to ensure that the only lambda terms you can write down are lambda terms that cannot possibly do any computation. That's to say, this is the grammar of normal forms. That's to say, things you could end up in when you've finished reducing a lambda term. What's going on? We split, instead of just having terms, we have things called normal terms and things called neutral terms. And the idea of a neutral term is that it's something that has got stuck on the way to becoming a value. So you can see the normal forms, we say they're either a lambda, that's to say a function, so we're used to those being values, or a number, we're used to those being values, or it's neutral, which means it got stuck on the way to becoming a value. And let's look at what stuck things are like. A variable is stuck. An application is stuck if the function got stuck on the way to being a lambda. You can see, when I say in an application, the function has to be neutral. That stops the function being a lambda, which means there's no way to write down a beta redex. And then I'm a bit anal retentive about addition here. I'm saying that you either get stuck to the left of a plus. This is the first argument of the plus got stuck on the way to being a number, or the first argument to plus made it all the way to being a number, but the second argument got stuck on the way to being a number. So either way, that's never going to do any more computation, yeah? So I've carefully written down exactly the ways of getting stuck. So you know that when you beta reduce a lambda term until you can't beta reduce it anymore, or you reduce the lambda, do small step reduction till you can't do it anymore, you're going to end up satisfying this grammar. So you'll notice that lambda has ended up in the normal rules, and that application has ended up in the neutrals. And that's typical. In particular, also you see that the values have ended up being on the normal side. And the things that compute with values have ended up being in the neutral side. So neutral things are computations that have got stuck because you didn't get a value. Okay? The marvelous fact is that you can always, for terms in this grammar, you can always do type checking for the normals and type synthesis for the neutrals, and you will never have to make anything up by magic. Remember, we said that it was, when I do type checking, I always write the type first, because the type comes first when you're doing type checking. And I say, does this type accept this thing? So, can we push the type sigma arrow tau into this lambda term? Well, we can if giving x sigma, we can push tau into t. We can push the type of natural numbers into a number, and here's the rule that says if we're trying to push a type into a neutral, well, the idea is neutrals we're going to synthesize types for. So how do you push a type into a neutral? You actually say, synthesize the type for that neutral, and then check that the type you got is the same as the one you want. See what's going on here? And then for the neutrals, we can always do type synthesis. How? Well, if we start with a variable, to do type synthesis for a variable, you just look it up in the context. The context is sitting there telling you the types of all the variables. So you can just look it up. We said to synthesize the type for an application, you synthesize the type for the function. And that tells you both what type of argument is expected and what type of result to give back. So we now know how to check the argument. By synthesizing the type for the function, we learned how to check the argument. And we also learned how to synthesize the type to give back overall. And it's less interesting for plus. So there's this weird thing that you don't need any kind of creative, just invent a type from nowhere if the thing that you're trying to check is okay has already stopped computing. If it's already in normal form, figuring types out is no bother at all. All the trouble comes from figuring out types for things that might actually compute. So there are various ways we can get around this. So this is very much what Stuart has been up to for as part of his PhD, so he's the expert here. One thing you can do, right, so here's a rule that says if you've got a neutral term, it becomes a normal term, and it's dead easy to check a type because you can even figure the type out. So you just say, when we figure the type out, is it the type we wanted? The grammar is very careful not to go the other way around. You can see here, neutrals are embedded in normals, but not the other way around. So think about what that would do for us, right? If we were trying to do it the other way around, then we would have to say, oh, I've got this normal term.
Can you zoom out, please?
Yeah. I've got this normal term. I want to figure out a type for it. The only thing I can do is push a type into it, but I've got no idea what type to push into it. And correspondingly, no idea what type I'm going to get out. When you go from neutral to normal, you've got two ideas for the type of the thing, and you just have to check that they're consistent. When you go the other way around, you've got no ideas for the type of the thing, and you're in deep trouble if that's the way you want to play it. So we don't do that, but what we can do is to say, if you give a normal term a type annotation, you can treat that as a neutral. So how do you synthesize the type for this? You first of all check that the type is good. You check that the type tau really accepts the term t, and then you can just give it back. So that's to say, so if we do that, right, remember, I just showed you that the grammar wouldn't let you write anything that looked like this. It wouldn't let you write a lambda as a function in an application. I was carefully writing down things that are stuck. But now if I allow type annotations, I can write this. So in this slightly reorganized system, anywhere you're actually writing down something that would compute, there's always a type annotation. And that's the type annotation that tells you how to check this lambda and how to synthesize the type of the whole application. So one way to get out of having to do anything clever to figure out how to synthesize types for lambda terms is simply to insist on putting type annotations in crucial places. So that's to say, if you don't want the computer to have to make stuff up by magic, you're going to have to give it a little bit of extra information. So if you put type annotations in the right places, the computer will never have to guess stuff. Okay? So there's another way of doing it which boils down to the same thing. It's actually perfectly sensible. When we write programs of any size, we always make definitions. So we define, we give names to functions. We say, I don't know, we say things like, twice is equal to lambda f, lambda x, f of x. We don't want to write out massive formulae, so we allow ourselves to make definitions. And you'll notice that the body of this definition has no beta redexes in it. The body of the definition is a normal form. If you're happy to write type annotations for definitions, like twice takes not to not to not to not. If you're happy to write type annotations for your definitions, then and you're happy for the body of your definitions not to have any beta redexes in them, then you're again providing enough type information for everything to be worked out. So what we're basically saying is, like, if you're willing to write proper documentation in your source code that consists of the types of the things that you're defining, then you never need to do anything clever, or a computer never needs to do anything clever to figure out types. So that's two different ways to reorganize lambda terms to get out of having to do anything clever to figure out types. So I mention those things only for essentially cultural reasons. Let's now look at how to be clever, right? Which is what computers really do. Let's go sideways, partly because we can zoom in. Right. Am I on the screen? Good. We start with the empty context. Let's try and figure out what type this thing has. You'll notice it's got a beta redex in it. The takeaway from the stuff I was saying at the start is these problems are only difficult if they've got beta redexes in them. Okay. So, at the moment, we've got no idea what type this thing has. But we do know that our only chance to give it a type is to use the application rule. So let's use the application rule as far as we can see. Make my line a bit longer. So there's lots of missing information. But we're hoping right, so what I'm saying is, I hope you agree, that if we're going to be able to make a typing derivation for this thing, it is going to look like this. We've got plenty of blanks still to fill in, but this is the only game in town. Okay, let's truck on. We've got to now figure out the type of this function. Our only chance to figure out the type of this function is to use the lambda rule. So let's write down as much of it as we can. X is going to be given some type or other, and then we're going to try and figure out the type of the body of the function, and that's X. Okay, so here's the deal. What computers do in this situation, if they don't know what type to write, they just make up a variable that stands for the thing they don't know. And I'm going to use question marks with a numerical subscript as the variables. And that way, I can always make new ones because I can always pick another number. So we don't know what type to give X, so we'll just make up a variable that stands for that, which I'm calling question mark 0. So our syntax of types now has been extended with these variables in it that just stand for things we haven't figured out yet. Okay. Are we now in a position to figure out the type of X? Well, in as much as we at least have a name for it. So we can use the variable rule to give back a type for question mark, for X, that's question mark 0. Okay? And now we can fill in the next bit. We're good. We can give the type of this lambda term, lambda x arrow x. Well, according to the lambda rule, that type should be question mark 0 arrow question mark 0. That's to say, we have figured out that the identity function takes some sort of thing and gives back that sort of thing, but we haven't figured out what sort of thing. Okay? Now, if we play the same game for the argument, what will happen? Exact same deal. We've got to make up a type for y. This time, anytime you make up a name for a variable to stand for a thing you don't know, you have to pick a fresh name. So that's going to be question mark 1. And then back comes question mark 1. And here we get question mark 1 arrow question mark 1. Okay, now we've figured out the type of the function, we've figured out the type of the argument, but for this to be a valid application, something else has to be true. What else do we need to be true? the argument has to be the kind of thing that the function expects as an input. So that tells us that we have a constraint. We need question mark 0 to be equal to question mark 1 arrow question mark 1. So the application rule says we've got to satisfy this constraint. So what do we do? Well, this constraint is very easy to satisfy if we just decide to take question mark 1 arrow question mark 1 as the definition of question mark 0. Right? These were things we don't know. We've just got a constraint that tells us what one of them is. So now what we do is everywhere, and I didn't leave myself enough space because I'm a numpty, we substitute question mark 1 arrow question mark 1 for question mark 0. So I'm just going to write a pair of dots here to say, let us assign question mark 0 the value question mark 1 arrow question mark 1. So this type here has now become question mark 1 to write lots of arrows in. And some parentheses. Yeah? So the constraint tells us what substitution we have to make. And then we know that when we plug in, now that we've satisfied the constraint, we can give back the type of the whole thing, which is question mark 1 arrow. I seem to have given up worrying about whether my arrows are red or blue. So we figured out that the whole thing gives us back a function, right? We're applying the identity function to the identity function. We're definitely getting back a function. That function definitely inputs some type of thing and gives back the same type. We don't know what type, yeah?
Why aren't the parentheses around the second pair of question mark 1s?
I'll put them in. By convention, arrow associates to the right. So that's to say, the usual, if you've got, so usually when you write something like A arrow, B arrow, C, you mean a thing that takes an A and a B and gives you back a C. So you don't have to write parentheses in a thing like this, and it means that. So I was just leaving out parentheses that weren't forced on me. But it actually does make sense to put them in here and say, yep, this identity function is an identity function that is being fed a function and giving back a function. Okay? So we just made up variables for the things that we didn't know, and we followed the rules, and we collected the constraints that were forced upon us, which were equations that involve those variables. We solve those equations, and that tells us what some of the unknowns are. But it might not tell us what they all are. So for example, here, we never did figure out what question mark 1 was. But that's okay. If you get to the end of doing this, and there are some variables still unsolved, that just meant there weren't any constraints forcing those variables to take particular types, to be particular types, which means you are free to make them whatever type you like. You know, we can now choose any type we want question mark 1 to be, and we know that this derivation will be good. Like we could substitute the natural numbers for question mark 1, and this typing derivation would still be fine. We could substitute some more interesting type for question mark 1. This derivation would still be fine. Okay? So what we do is introduce variables for things we don't know and solve the constraints. Right, so let's focus on solving constraints. This is an algorithm from the 1960s, which everybody should know. That's to say, that's not me saying, goodness me, if you don't know this algorithm, you're a numpty. That's me saying, where's my phone? That's me saying, I'm evangelical about this algorithm, and I want everybody to know it. But I should, maybe because I need to kick you out so you get to Sartorius' test on time. You're saved by the bell. Basically, when you've got an equation involving type variables, how do you solve it? There's 6 rules that tell you what to do in every case. Sometimes you win, sometimes you lose. Just follow those rules mechanically, and you'll solve the equations. That's what computers do when they infer types, and they are in the notes. Anyway, thanks for coming. Good luck with Sartorius' test.